The rock shouldn't have existed. Not there, not in that shape, not with that mineral hiding inside it. For months, the scientists working on NASA's Perseverance rover had been staring at the floor of Jezero Crater, certain they understood what they were looking at, certain the story of this ancient Martian basin was already half written. Then the rover ground a small circular patch into a rock nicknamed Brack, pointed a laser-guided X-ray instrument at the freshly exposed surface, and the data that came back made a veteran planetary geologist admit, in his own words, that he had begun to despair he would ever find the answer. What that instrument revealed inside an unassuming gray rock on the floor of an ancient lake bed would end up rewriting the opening chapter of Mars's geological history. This is the story of Perseverance's first year on Mars, and the rocks that left its own science team stunned. To understand why a rock could shock a team of Mars experts, you first have to understand what they expected to find, and why they were so confident about it. In February 2021, Perseverance touched down inside Jezero Crater, a bowl nearly 45 kilometers wide, punched into the Martian surface by an asteroid or comet billions of years ago. Long before the rover ever left Earth, orbital images had shown something remarkable about this crater. A fan-shaped delta of layered rocks spilling into it from a breach in the crater wall, the unmistakable fingerprint of a river system that once emptied into standing water. Planetary scientists look at deltas on Earth and see slow, patient accumulation, sediment carried by moving water and dropped grain by grain as the current lost its energy. Seeing the same shape on Mars was enormous. It meant Jezero had almost certainly held a lake, fed by rivers, for potentially long stretches of time. And on Earth, wherever you find ancient lake beds, you often find the best preserved evidence of ancient life, locked inside fine sediment that settled undisturbed for millennia. That was the whole premise of sending Perseverance there in the first place. It wasn't chosen at random from thousands of candidate landing sites. It was chosen because if Mars ever hosted anything alive, a lake bottom was one of the most promising places on the entire planet to go looking for the evidence. So when Perseverance rolled off its landing platform and began exploring the crater floor, the assumption baked into years of planning was straightforward. The rocks beneath its wheels were expected to be sedimentary, the compressed, layered remains of mud, sand, and silt carried in by that ancient river and deposited on the lake bottom over long periods of time. Sedimentary rock is exactly the kind of material astrobiologists dream about because it can trap organic material, chemical traces, even the physical textures left behind by ancient microbial activity, and hold on to them for eons. The entire scientific game plan for the crater floor rested on this expectation. Then Perseverance actually got a close look at the ground it was driving on, and nothing added up. Instead of the layered, fine-grained texture of sediment settled at the bottom of a lake, the rover's cameras and instruments kept finding rocks riddled with large, chunky crystals, the kind of internal structure that doesn't come from sediment slowly piling up. It comes from molten rock cooling. This was the first crack in the story the mission had told itself before landing, and it opened an entirely new mystery. If this wasn't ancient lake mud, what was it? The rover's science team pushed into a region called Seda, a rugged, boulder-strewn area that had been particularly difficult to reach because of its terrain, full of sand ripples that could easily have trapped the six-wheeled rover if it drove in carelessly. It was worth the risk. Inside Seda, and especially in a subregion the team nicknamed South Seda, Perseverance found bedrock unlike anything the mission had planned for. Here is where the rock called Brack entered the story. Using its robotic arm, Perseverance ground away the outer, weathered surface of the rock to expose fresh material underneath, a process called abrasion, essentially sanding down a small circular patch so the instruments could see past billions of years of dust and radiation damage to the rock's true composition. Then it turned an instrument called Pixel toward that abraded patch. Pixel stands for Planetary Instrument for X-ray Lithochemistry, and it works by firing a tightly focused beam of X-rays at a rock's surface and reading the elemental fingerprint that bounces back, essentially building a detailed chemical map at a scale finer than a human hair. What Pixel found inside Brack left the team almost speechless. The rock was packed with unusually large crystals of a mineral called olivine, some of them engulfed within a second mineral called pyroxene. On Earth, olivine is common deep inside the planet, a major component of the mantle, the hot, slow-flowing layer beneath the crust. It is comparatively rare to find large amounts of it exposed and intact on a planetary surface, because olivine reacts easily with water and tends to break down chemically when it's exposed to wet conditions over long stretches of time. Finding an abundance of large, well-preserved olivine crystals told the science team, unambiguously, that this rock had not formed the way they expected. It hadn't been laid down slowly as sediment, it had crystallized directly from molten magma, and the size of those crystals mattered enormously, because crystal size is a kind of geological clock. Small, hastily formed crystals suggest lava that cooled quickly at the surface like a puddle hardening in the open air. Large, well-developed crystals, the kind found in brack, suggest magma that cooled slowly, likely trapped underground in a chamber, insulated from the cold Martian atmosphere, taking a much longer time to solidify. This was the moment the project scientist, Ken Farley of Caltech, described as finding the smoking gun. Not because it disproved the presence of an ancient lake, orbital images of that delta weren't going anywhere, but because it revealed the floor of the crater itself, the ground the lake had once sat upon, was not the sediment everyone expected. It was igneous rock, born of fire rather than water, and quite possibly the exposed remnant of a slowly cooled magma chamber, or the solidified remains of a thick lava lake that had once filled the crater floor before any water arrived at all. Why does that distinction matter so much? Because igneous rocks are, in a very real sense, natural clocks. Locked inside their crystal structure are radioactive isotopes that decay at fixed, well-understood rates, allowing scientists to calculate almost precisely when that rock originally solidified from molten material. Sedimentary rocks, built from recycled fragments of older material, don't offer that same precision. You're often just dating the age of the particles that happened to wash in, not the moment those particles first formed. By confirming that Jezero's crater floor is igneous, Perseverance handed future scientists an actual timestamp for one of the most important surfaces on Mars, a fixed point they can use to anchor the entire geological timeline of the region, and by extension, help calibrate the age of surfaces across much of the planet. But the Olivine discovery was only the beginning of what made this first year so disorienting, in the best possible sense, for the mission's scientists. As Perseverance kept exploring and abrading rock after rock, a second thread of evidence began weaving itself into the story: water. Despite this bedrock being igneous rather than sedimentary, it was not untouched. The instruments found clear signs that water had interacted with these rocks, not once, but apparently on multiple separate occasions across Martian history. Some of the minerals detected only form in the presence of liquid water. Salts, sulfates, and other water-altered compounds had crept into cracks and pore spaces within the volcanic rock, evidence that even after this magma solidified deep underground or as a lava lake, water later moved through it, reacted with it, and left its chemical signature behind. This turned a simple story into a genuinely complex one. It wasn't as though Mars had a purely volcanic phase followed by a purely wet phase in some tidy sequence. The evidence suggested overlapping, repeated episodes, fire and water intersecting more than once over an enormous span of time. Imagine a house built from stone quarried out of an old volcanic outcrop, and imagine that stone, decades apart, being repeatedly rained on, repeatedly flooded, its surface slowly reacting and changing with every soaking, while still holding on to the bones of its original fiery origin. That's roughly the layered, messy history now being read out of the floor of Jezero Crater.
And then came the detail that more than any mineral or crystal made headlines around the world. Using another of the rover's instruments called Sherlock, short for scanning habitable environments with Raman and luminescence for organics and chemicals, the team detected organic molecules within these rocks. It's worth pausing here, because this single sentence tends to get misunderstood the moment it leaves a laboratory and enters public conversation. Organic molecules are not proof of life. In chemistry, the word organic simply refers to molecules built primarily around carbon atoms, and carbon-based chemistry is genuinely everywhere in the universe, found in meteorites, in interstellar gas clouds, in processes that have absolutely nothing to do with biology. Organic molecules can form through purely non-living chemical reactions, especially when volcanic activity and water interact, which, as it happens, is exactly the kind of environment Perseverance had just found strong evidence for in this very location. So no, this was not a discovery of life, and no responsible scientist on the team ever claimed it was. But it mattered enormously anyway, because organic molecules are the kind of raw material that life, wherever it exists, tends to use as building blocks. Finding them confirms that Jezero Crater once had the right ingredients present, at the right time, in an environment that also had liquid water moving through it, and volcanic activity supplying heat and chemical energy. None of that guarantees anything ever lived there. But it means the necessary chemistry was on the table, which is precisely the kind of environment astrobiologists spend their careers hoping to find, because it's the only kind of environment where the search for ancient life is even worth conducting in the first place. While all of this chemical detective work was happening on the surface, Perseverance was also quietly building a picture of what lay beneath its wheels using an instrument called RIMFAX, the radar imager for Mars' subsurface experiment, the first ground-penetrating radar ever deployed on the Martian surface. As the rover drove, RIMFAX sent radio waves down into the ground and listened for the echoes bouncing back off buried rock layers. building something like an ultrasound image of the subsurface, reaching down roughly 10 meters below the crater floor. This gave scientists something orbital cameras could never provide: